Unfortunately, I got into a cycle of washing boards, and I washed off all the boards I used today after the one we just saw, but we can reconstruct what's going on. And I want to kind of take off on some of the responses I got in the chat. Okay, so you have a pendulum. You know what the situation is here. Your small angle approximation is that the pendulum moves in a horizontal direction. And since this angle is small, the vertical component, the y component of the tension, is equal to the weight. So if we project the tension over here, we have the Ty, and here we have the Tx. So the tension is equal and opposite to the weight, because if the pendulum moves only in this direction, we have vertical equilibrium, so that the weight and the T, I'm saying Tx, Ty up here, the y component of the tension are going to be equal and opposite, and the tension vector is going to be so close to this that the tension is going to be equal to the weight in the approximation. And then the Tx is just this component of the tension, which is related to the weight in the obvious manner. And we get a nice, neat, and easy model that we can use to analyze the motion of the pendulum for small angles. So that's only a small angle approximation. The pendulum descends, so it's not really in vertical equilibrium. Now, if it descended at a constant rate, it would be in vertical equilibrium, but the rate of descent is not constant. If we release the pendulum, it starts, a rate of descent is initially 0 until it builds up a little speed, which it does instantaneously. And then when it runs through equilibrium, its rate of descent is again 0, but it descended. So if you descend at a rate that starts at 0 and ends at 0, and if the average rate of descent is not 0, then the descent isn't always 0, so the descent is certainly not at a constant rate. So if you understand that argument, there's an argument that says we don't have vertical equilibrium. The actual situation is close to the, the actual situation is depicted here, and in this case we drew the x and y axes in such a way that that we assumed y equilibrium, that the only motion would be in the x direction, the only acceleration would be in the x direction. That's not so. If we draw with this coordinate system, then we can analyze the forces a lot more accurately. We put the x-axis in the direction of motion, perpendicular to the y-axis, which is in the direction of the string. The weight vector resolves into y and x components, much like it does on an incline. And I mention this for two reasons. One, it is accurate, and two, this did cause a little confusion in some of your responses that we'll get to in a minute. If you do this, you get this very accurate picture, and the weight vector is the weight vector is going to be the net force vector, because the y component of the weight and the tension will add up to 0. So there's your net force. So here's your net force. That's your x component of the weight. Now, if you have a small angle, then if you project the weight onto the horizontal direction, it's going to be very close to the x component of the weight here. But if you get away from horizontal, that's no longer the case. Now, the problem with this model is it's much more complex, because as the pendulum moves, the xy coordinate system changes. So you're analyzing something with a changing x and y coordinate system, whereas here you have a fixed x and y coordinate system. So this model is much, much simpler to deal with than this model. Now, there was a little tendency to confuse the tension force with a normal force, and that's very easy to do because it kind of feels the same. But if you think of the source, it's different. A normal force is where you're pushing into some material, and the material is pushing back either by an elastic reaction that pushes back perpendicular, or a compression reaction that pushes back perpendicular to the surface at which the force makes contact with that material. Okay, so while the tension and the weight line up like a normal force and a weight, you really don't want to think of it that way, because what that's going to do, among other things, is that's going to evoke this picture. And this picture gives you a order of magnitude more difficult model to analyze, as we'll see before too long. This gets into a very complex differential equation, whereas this model, this simplified model, gets into a very simple differential equation. I could take 5 minutes and show you that differential equation right now, and I believe you'd understand it. But we'll get to that in good time. I've been tempted to do it a couple of times already, but I'm holding myself back. Okay, and this is it. Whether you impose your coordinate system like this or like this, the tension and the weight vectors are where they are. And among other things, we see that these forces can't be equal and opposite because they aren't along the same line. The tension and the weight vector are not opposite. Now, some people said they are. Well, you want to be very specific. You're kind of in the right ballpark. The magnitude of the tension, the magnitude of the weight vector are pretty much equal. But we have this approximation, the small angle approximation. It's the component of the tension vector along the line of the weight vector that's going to be opposite to the weight vector, and even that isn't really true. The truth is down here, where the tension is equal and opposite to the projection of the weight vector on the direction of the tension. So this picture is approximate, this picture is exact, but again, this picture is the one we can analyze in this course. We really can't analyze this. Late in the differential equations course, you might well see something like this. Okay, so again, backing up, there are a couple of mistakes, or a couple of ways of thinking that you really don't want to get into at this point. Okay, and that is, again, thinking of this as kind of a normal force and thinking of tension and weight vectors as being opposite. You want to qualify that. You want to be sure you see where the approximations are occurring. Another thing that I saw, some people listed acceleration as one of the forces. And there are only two forces acting on this pendulum if you assume that there's no air resistance or other forces. In the ideal case, there are only two forces. They don't line up. You get a component that well, your net force is going to be the sum of this force and this force. You could do a vector sum. That vector sum would look something like this, so that here's your resultant. Okay, here's your tension, here's your weight, here's your resultant. And the resultant isn't really horizontal, it's close to horizontal, it's actually down like this, etc. Okay, another comment we saw, and again, there's good thinking on all these responses, but the dot product of the weight and the tension, somebody made the comment that the dot product of weight and tension would be the net force. I know what you were thinking, but if you think the dot product of the weight and the tension, in the first place is going to have units of force squared. In SI units, that would be Newton squared. Well, your net force doesn't have units of Newton squared, so the dot product of the weight and the tension is not going to be the net force. The net force is a projection of the weight perpendicular to the tension and in a very specific direction that I didn't bother mentioning, but that's kind of what you were thinking about. And of course, when you think projection, you're using the dot product, so it's very easy to kind of shortcut the details of your thinking and make a statement like this when what you're thinking of is exactly the right thing, which is this. You want to be sure that you pursue the complete details of your thought, though.